Welcome to my Texas workshop. I'm Randy Lammers.
I'm Aaron Keevan.
This is worth knowing. So the last time we talked about torque is primarily a rotational force to overcome friction. And we did some demonstration on that. I think we proved that very well, Aaron. We're at about 32% on that particular lot that we did our testing on. Today, what we want to talk about is really how then do we accomplish a clamp load and control those rotational forces.
Sure, Randy. I think before we start into this conversation, we need to take a look at the yield strength and ultimate tensile strength of a fastener. Those are tensile properties that we use for fasteners. So
Exactly.
when we talk about the tensile strength and the ultimate tensile strength, that's where it ultimately fails, the ultimate tensile strength. So
Correct.
We've stretched this bolt as far as it could go, and it is done. Now, when we talk about the yield point, we're talking about a transition from elastic stage to a plastic stage. And in the plastic stage, that fastener is gone past its point. It can no longer go back to its original shape. In the elastic stage, that's where it acts like a rubber band and will go back to its original shape. So,
Oh my gosh, that reminds me of another Uncle Mo story. Good old Uncle Mo. Every year, Mo has a big family reunion. It's 8 hours from Houston, Texas, out to far west Texas. And we load the family up in the car, we get out there, we do the whole make nice and hug and kiss with all of the relatives and so forth. And I look over across the room and Mo's on the other side of the room. And I look over at my cousin Don, Mo's son. I said, Don, he's up to something. He goes, oh, yo, Randy, he's been waiting on you all day. He can't wait for you to show up. So I go over there, I reach out my hand to shake hands with him, and he just grabs my hand and starts pulling me towards the barn. And there we go. He grabs a manual on his way by, and through the barn we go, and out the other side of the barn. On the side of the barn, he has who knows what piece of agricultural equipment laying out there. And he opens the book and he goes, here it is, Randy. Here's the torque. Here's my torque wrench. I did exactly what you told me to do. And look at this bolt. Mo, let me have your bolt right here. Okay, if you can imagine, look at that bolt, Aaron. Is that just the prettiest bolt you've ever seen?
that's a pretty good example of necking, that's for sure.
That's just a pretty hourglass, isn't it?
Yep.
And he starts off, here you go, Randy. You're selling these cheap-made bolts again, made out of cheap-made steel. Well, I looked at the end of that and I said, Mo, that's a grade 8. That is high-strength steel. That's good quality steel. That's not what's happened here. Now, he's out in far west Texas, just shy of the desert. You used to live out there.
Yeah, 10% humidity, 100-mile-an-hour winds.
Exactly. And everything dries out. I mean, it says, if it tells him to put 1 squirt of grease, he puts 10 squirts of grease. His idea is just to grease everything, and your joints last longer that way.
Right. Yeah, don't let the finish do the work anymore.
Exactly. Just put grease on there. As a matter of fact, he's on me about every time I get on my tractor, he says I need to grease it. Every time I get on there, I'm like, oh my gosh, Mo. Okay, so I look down and here's all this grease around that joint. I said, Mo, when you bought that, did it have all that grease around that joint? And he goes, oh no, that was just pretty painted and it was shiny. I said, exactly, Mo. I said, the torque that's in that book is the factory torque. If everything was the same, that would work. But now that's changed. You've put that grease there and look what you've done. You've taken this part into yield. It's good steel, it's a high strength bolt, but you've taken it into yield.
Well, and Randy, that's because Mo really didn't understand that yield strength and really good engineering design. You want to go to about 75% of the yield strength of the fastener, and that'll give you that safety margin that you need in order not to go into that plastic range and stretch it.
Absolutely. That's good on hard joints, not soft joints, but on hard joints. That's exactly right. So fasteners act like coiled springs. So what they do is when you apply that load, that steel actually stretches just like a coiled spring. When it wants to go back to its original length, that's where the clamp load happens. So we have what we call Hooke's Law. and we operate on Hooke's Law all the time. Hooke's Law teaches us that for every 30,000 pounds per square inch of stress applied to the fastener, creating that stretch, that the steel will stretch 1,000th for every inch between bearing surfaces. I'm going to repeat that. For every 30,000 psi of stress applied, steel will stretch 1,000th for every inch of material between bearing surfaces. Knowing that, we can do a mathematical formula and find out what our stretch length is to accomplish a given clamp load. And it's extremely accurate.
Right. And another way that you can actually verify this physically is by doing an ultrasonic measurement.
Yeah.
So they'll take any given fastener, like this grade 8 bolt here, and do a precise measurement, and then go back with the ultrasonic equipment and figure out how much stretch they actually accomplished during their installation.
Exactly. You know, Aaron, I had the pleasure of being part of an important meeting at the National Academy of Engineering in Washington, D.C., and there was a gentleman there that talked about just exactly that. And one of the things they do for our ships is they will use ultrasonic stretch measurement to put the blades on the ships, because that absolutely has to be precise. Now, they don't do a lot of that, but when they do it absolutely precise.
Critical application.
Critical applications. There's also another formula that has to do with torque angle, which is the angle of rotation. So after achieving a torque that creates just a snug fit, then you can rotate a very precise angle that will give you the stretch length of the fastener. Now, that's a little more complicated, so we're going to go into that in another episode in the future. But so we have stretch length, we have angle rotation, and you can actually accomplish good clamp loads that way.
Sure, but the problem is we're in high-paced production lines.
Yeah.
They don't have that sort of equipment on hand. Really, they have to utilize torque as a means to get to their clamp load.
Yeah, measuring stretch can be very slow. So torque, you can set your torque tools on the assembly lines. You're absolutely correct about that. So let's go back then and let's talk more then about torque. We understand stretch, but let's get to torque and achieving clamp load with torque. So there is a simple formula that most people use in industry. There's a long formula. Let's talk about the simple one, which is T equals KdP. So T is torque, and it equals K, which is the frictional factor of your joint.
Right. Now, the K is really important concept to understand too. A lot of people make a direct correlation to being the coefficient of friction. That's actually not accurate. The COF is really only applicable to primarily coatings. When we talk about K, we want to talk about the whole bolted assembly. So that's what, when we talk about the COF of coatings, it's zinc, nickel, dip spins.
Yep.
We've really got to take into effect all of those components together in order to understand that frictional factor.
Exactly. You know, Aaron, I've seen engineers on that subject right there actually look up and find the coefficient of friction of a given finish, and then they write a chart using that as their K factor in this equation. That's a big mistake because that's not correct. So I'm glad you brought that one up. So we have T equals torque, K is the frictional factor of your joint, D is the fastener diameter basic, and P, which I also see written as F sometimes for force. So P or F is the preload, which equivalent then is the clamp load of the joint. So T equals KdP. Right. That's the formula. It's a very simple formula, and it works very, very well in most applications. Okay, Aaron, so we know that T equals KdP, so let's figure out what load we want then for the setup we have on our load cell, which is a 5/16 hex head cap screw.
Okay. Yeah, that's a SAE grade 5 or Society of Automotive Engineers, J429 is the spec there.
Right.
And in that standard, the minimum yield is 92,000 PSI.
Correct. So, but we need to get to straight load. So PSI times tensile stress area will give you straight load.
Right.
So what's a tensile stress area?
52 thousandths or so. It actually is 52 thousandths. You can get there again, long formulas, but
Yeah.
Go back to the IFI, it's going to tell you that information.
Yeah,
So.
look this one up in a chart, guys. So, all right, so 92,000 PSI times 0.052, it gives us our straight pounds. In this case, that would be 4,784 pounds. Let's just round that off to 4,800
Yeah,
for
it
our...
makes it easy for calculations for sure.
So we have that. So 4,800 pounds of yield strength then is what we have.
And we're not completely done there, Randy, because we do
Okay.
need to get to that safety margin we talked about earlier. So we need to take 75% of that value. So what does that come out to?
3,600.
All right.
So let's go over to our load cell and let's do that.
Yeah, let's do it.
3,600. Okay, Aaron, let's take a look at what we have here.
Well, last time we used torque that you provided from our chart to see what kind of load we got on our load cell.
Correct.
So this time, I think we should do a little bit different, and we can actually figure out what the frictional factors are going to be here. So that K value.
That K value, yeah. So we'll run to a load and see what torque it takes to get to that load. So let's do that. But first, Aaron, we have our safety.
Of course.
So as always, we wear our safety glasses, so PPE, in order to always stay safe. And as you want to go ahead and start doing a setup, let me reach down here, and there's a calculator, and we'll grab our pad, we can write this down for it with.
Sure thing.
All
Get
right,
this
so
set up.
we are utilizing the same lot of fasteners we used in the first episode, so maintain that lot control. And so same setup, we put the hardened washer against the load cell, a regular flat washer against that, and then snug that up. So what we want to do this time, Aaron, is see what torque it takes to get to 3,600 pounds of force.
Sure.
So
I
just
always
get it
bring a
snug-
little indication there. I'm going to turn this on now. Make sure we're at 0, of course.
Okay.
And now I'm going to set us up, and you said 3,600 pounds of torque.
3,600 pounds of torque, Aaron.
Or
Let's get
3,600 pounds of
a
force.
force.
Man, we can't confuse ourselves. Let's see, where do we get?
3,600.
I got 250 inch-pounds of torque.
Okay, let's write that down. What was that? 200 and what?
50 inch-pounds of torque.
250 inch-pounds of torque. Okay.
I'll loosen this up, Randy.
Yeah. Here, I'll go ahead and grab another one because we always want to make sure that we do use a fresh fastener every time. You burnish that threads a little bit whenever you load one up. So each time let's use a fresh hex head cap screw. We'll set that one off to the side, put the other one on, and our flat washer, and then our nut. Okay,
Same
snug
deal.
that up.
Yep, get it to,
3,600
just
pounds.
give me a little indication there first.
Okay.
Turn on my torque wrench, or make sure we're zeroed out. All
And
right,
3,600.
3,600. Randy, I've got 333 inch-pounds.
Okay, a little frictional factor difference on that one, so I'll write 333 down. And let's do one more and see what we come up with. As you do that, I'll grab this. So frictional factors change. We proved that in the first one. So we've got our target load, but what torque do I use? That's the big question that we get from customers all the time. What torque do I use? They're calling us, asking us this question. So here's our new fastener. You put your hardened washer on there. Put this against the load, against the hardened washer. Put a nut on there real quick. And let's see what we get for a third test.
Same snug here.
Yep.
Just get it there. All right, got a little indication. All right, it looks like we're ready to go. Get to 3,600 pounds of force. Holy smokes, Randy, we went up to 364 inch-pounds.
364. Okay, so let's run our calculations on that and let's see what we get in terms of what then would be the K factor, because we're talking about T equals KDP. So now we have torque at 250, 333, 364. We have our P, which is 3,600.
pounds. Force, yep.
So we know our diameter of fastener, it's 5/16, so that's 0.312. So if T equals KDP, then K equals T divided by DP. So let's solve for K. So we take 250 and we divide that by 0.312 times 3,600, then that's going to give us that K factor.
So what did that give you, Randy?
So at 250, that's a 0.22 K factor. At 333, that's a 0.30. And at 364, that's a 0.32. Wow, that is 31% variance.
Yeah, that sounds pretty familiar. It's kind of similar to what we had in our first round of testing.
What are we going to do now
Randy,
about that?
hold on, I got an idea here, right? So maybe
Okay.
we can actually do something to help control the frictional factors.
Of course.
Think about that.
Okay, you're going to use my chapstick?
Yeah, I've got to use it. When
it's
you
wax.
use the-
Okay.
We'll see. I think my theory is going to hold true here. So,
Okay, well,
got to get
let's-
this loosened up first.
All right, let's undo one. So exactly, so what do we do next? We control the frictional factors. Well, how do we control the frictional factors? By purposely using a lubricant that we know the coefficient of friction of. That's what we do. So you can take your zinc plating, you can put a torque modifier on that is a controlled lubricant, or you can also change to maybe another fastener finish that is more controlled. As an example, on the dip spin coatings, the ASTM specification now controls that COF of the dip spin coatings to about a plus or minus 0.04. Much smaller scatter than what we're used to seeing with the dry joints like zinc plating as an example. So what Aaron's about to do is to put some chapstick. Yeah, I know, it's kind of funny. So put the chapstick on there. That's a wax, that's a controlled COF. So 3,600 pounds of load is our target. We've now controlled our coefficient of friction, or our K factor in our joint just a little bit more. Let's see what we have here. 3,600 pounds of load.
Little indication there, Randy. Just give me a
right.
second.
All right,
All right. Good to
get your
go.
torque wrench on.
Yep.
Okay.
Make sure. Yep, I've got it on. Going to 3,600. Perfect.
Okay, what's your,
Came out at 172 inch-pounds.
oh my gosh, that's a big difference. Okay,
it sure is.
172. All right, well, that's a big difference.
Well, it's easy to turn that
So
thing
that
too, I can tell you.
chapstick really did a nice job of giving a lubrication there. Now that's less wear and tear on your people on the assembly line because they're not using as much torque.
Yep.
So that's better on your tools, better on carpal tunnel syndrome, issues like that we run into on the assembly lines. So it adds a lot of other benefits to it as well. So let's get the other one set up. Again, we're just putting this on the thread section. Now, you control all of your pieces with the lubrication. You're really going to control everything. Because again, 40% of the torque is to overcome the frictional forces of the thread.
Threads.
We still have the bearing surface to contend with. But let's just see what this does by itself. This is a simple way to run this test. All right, a little chapstick on the thread section. Not to do much, because the nut's going to actually push that chapstick on down. In other words, if you did a wax, for example, and some customers will do that. They'll just wax the parts. We can do that in the electroplating. After electroplating, you can do a wax dip. That's another way of going about this. It's very economical, very simple to do. You don't have to do this on the assembly line.
I'm gonna set up here, Randy.
All right,
All right. Let's get
now let's see what we have here. 3,600 pounds.
All right. Again, get to a little indication on our load cell. All right. Make sure my wrench is on.
At 0.
Sure is. At 0. Taking it to 36. Perfect. I got 165 inch-pounds.
Okay, 165. A little bit more lubrication on that one. We'll do a third test. We always like to run 3, just to kind of, that way you kind of give the upper and lower and a mid-range to see what's kind of happening with the.
Try to get this off quickly.
Certainly, the more tests you can run, the better off you're going to average this out. We typically tell customers, by the way, while he's setting this up, is to run test on a joint. And that's the best way to go about it. Find what your range is in your particular joint. So typically I teach to do an experimentation of about 10 tests. Run your failure, find your failure mode. You'll be amazed how many engineers don't understand what failure mode is on a particular joint. So run to failure, say, here's my failure torque. Failure can be embedment, failure can be something else in the joint going wrong, or failure can be Uncle Mo taking it into yield. That can also be a failure, or certainly breaking the fastener. So find your failure, back off of that. We typically tell customers 35% as a safety margin, back off of that 35%, and you can use 65% of failure torque as your installation torque. That's a very simple way to do it.
Getting
So
pretty
let's
close
see
here.
what test number 3 ends up to be.
Get a little indication on the load cell again.
Okay?
All right. Now, let's take us up again. 3,600. Go, baby, go.
Okay, what do you have?
This is great. 154 inch-pounds.
154. So 172, 165, 154, certainly lubricated joint.
Much better.
We're at, now we run our calculations again up on your screen. So we have 172. We're going to take this to 3 decimal places so that we can actually see the full thing. So that's a K of 153, 165 is a K of 147, 154 is a K of 137. That comes out to a 10% variable, much different than a 31%. So by controlling those frictional factors, using something as simple as chapstick or wax to control the frictional factors only on the thread section here, that went from 31% to 10%. Big change.
Yeah,
big
huge change. And that's what it's all about. If we can get there with us controlling those frictional factors, we're ultimately going to have better control of our clamp load.
And we'll get the clamp load we look for every time. Absolutely. So control the frictional factors, you control the torque to tension relationship. So Aaron, in conclusion, we control our frictional forces, and in this case, our chapstick did a very good job for us. We went from a 31% to a 10%. That's important.
Yeah, sure is. I mean, when we use that type of lubricant, obviously it's going to help us to control those frictional factors all the way through.
And if we can do that throughout all of the pieces in the joint, that would be even better. So the fastener finish is important to this. So there's things you can do on the zinc plating.
Yeah, adding modifiers to that will definitely help. So it lowers that coefficient of friction and key in on those K factors.
Exactly. So I already mentioned the dip spin coating, so we are very excited about what's happening in the dip spin finishes, where that's being controlled closer to about a plus or minus 0.04. So that works really good for us. So the bottom line is frictional control equals clamp load control. Control your frictional force to control your clamp load. That's worth knowing.
If you like the content you saw today, hit subscribe and the bell icon, and we'll see you next time.